What exists at the edge of the expanding universe? The universe is expanding faster than the speed of light, stretching galaxies away from each other into an ever-growing void. But what happens at the edge of this expansion? Beyond the farthest stars we can see lies a realm that may forever remain out of reach, where light has not traveled and matter remains unseen. Scientists are piecing together clues from distant galaxies, cosmic radiation, and the subtle tug of unseen forces, revealing a hidden architecture that shapes everything we observe. As we follow these cosmic threads toward the universe's edge, we are confronted with profound questions about space, time, and what might exist just beyond the horizon of perception. Peering toward the cosmic horizon, when we lift our eyes to the night sky, the stars appear scattered like glitter across a vast, dark canvas. For millennia, humans have traced patterns in these points of light, crafting stories and mapping constellations, yet the notion of a boundary to the universe remained elusive. Ancient observers in Mesopotamia and Greece recorded planetary movements and the slow wandering of the stars, but the idea that the cosmos could stretch infinitely beyond human perception did not fully take shape until modern astronomy began to measure distances on an unprecedented scale. By the early 20th century, the night sky was no longer just a tapestry to admire. It became a frontier to explore, a canvas whose edges begged to be understood. The first hints that the universe might have limits emerged from careful observations of distant celestial objects. In the 1920 seconds, Edwin Hubble stood at the Mount Wilson Observatory in California. Peering through the 100-inch Hooker telescope, he noticed that galaxies, once thought to be static and confined within the Milky Way, were actually moving away from us. This expansion implied that space itself was stretching, carrying galaxies with it like dots on a rising balloon. Hubble's work transformed the abstract sky into a dynamic system, and with it came the question that would haunt astronomers for decades. If the universe is expanding, is there a horizon beyond which we can never see? Peering toward that horizon is complicated by the simple fact that light travels at a finite speed. When we observe a galaxy billions of light-years away, we are seeing it as it appeared billions of years ago. The light takes time to traverse the vast cosmic distances, meaning our view is a journey backward in time, as well as outward in space. This principle gives astronomers a natural boundary, often called the observable universe. Beyond this limit, light has not had enough time to reach us since the birth of the cosmos, and the regions that lie beyond remain hidden in what can only be called cosmic darkness. The observable edge is not a wall, but a shifting frontier. As time passes, more light reaches Earth from ever more distant corners of space, expanding our cosmic horizon slightly with every passing year. Yet this frontier is affected by the very expansion Hubble discovered. Some galaxies move away so rapidly that their light will never reach us. In this sense, the edge is not a static location, but a moving boundary shaped by the interplay of space, time, and the invisible force driving the acceleration of the universe's expansion. Astronomers have learned to read the faintest traces of this distant light, transforming what was once darkness into a map of cosmic history. Instruments such as the Hubble Space Telescope and the Planck satellite have allowed scientists to measure the glow left over from the Big Bang, called the cosmic microwave background. This radiation, first detected by Arno Penzias and Robert Wilson in 1965, provides a backdrop against which galaxies and clusters are silhouetted, offering subtle hints of the universe's large-scale structure. Even as technology has advanced, the question of what lies beyond the observable universe has shifted from mere curiosity to a profound scientific challenge. Theorists suggest that the cosmos may continue infinitely, with regions similar to our own or radically different in ways that defy imagination. Others consider the possibility that our observable patch is part of a vast multiverse, a single bubble among countless others, each governed by its own laws of physics. Humanity's attempts to peer toward the cosmic horizon are also shaped by our limitations on Earth. Light pollution, atmospheric interference, and the inherent faintness of distant galaxies challenge even the most sophisticated observatories. In this pursuit, there is both humility and exhilaration. The universe stretches beyond any vantage point we can occupy. Yet our tools and ingenuity allow glimpses of regions that no human could traverse. The edge of the observable universe represents not a boundary of matter, but a limit of perception, a reminder that the cosmos is larger, older, and stranger than any individual mind can fully grasp. As astronomers continue to refine measurements, build more sensitive instruments, and develop new theories, the horizon itself becomes a story of exploration, forever inviting us to look further and imagine what may lie beyond the light we have yet to see. The farther we peer into this cosmic distance, the more the universe hints that the edge is not a final destination, but the beginning of questions that may never be fully answered. The observable universe. The universe we can see is both immense and surprisingly structured. Through powerful telescopes, astronomers have mapped clusters of galaxies stretching across hundreds of millions of light-years. Each point of light represents not just a distant star or galaxy, but a story of formation, collision, and evolution that began billions of years ago. The observable universe, as scientists call it, is defined by the limits of light reaching us, creating a cosmic boundary shaped not by walls or edges, but by the travel of photons across space and time. Beyond this boundary lies what we cannot observe, but within it, patterns emerge that reveal the universe's history. Galaxies are not scattered randomly. They form filaments and walls separated by vast voids, creating a cosmic web that was first hinted at in surveys conducted in the 1980s. Projects like the CFA Redshift Survey, begun at the Harvard-Smithsonian Center for Astrophysics in Massachusetts, charted thousands of galaxies, revealing superclusters that twist and curve across the sky. These structures are snapshots of matter responding to gravity over billions of years, offering clues about the unseen forces shaping space itself. The scale of the observable universe is staggering. Current estimates suggest it extends roughly 46 billion light-years in every direction. This number is not derived from the universe's age alone, but also from its continuous expansion. The interplay between light's finite speed and the stretching of space means that many regions we see today were much closer when their light began its journey. Every image captured by telescopes is a record of a past we cannot visit directly, a reminder that observation in cosmology is as much about time as it is about distance. To peer deeper into this vast expanse, scientists rely on more than visible light. Radio waves, infrared radiation, and X-rays all provide different glimpses into galaxies, star clusters, and the cosmic background. Instruments like the Very Large Array in New Mexico and the Chandra X-ray Observatory detect signals that would be invisible to human eyes. Each wavelength uncovers phenomena hidden by dust, distance, or faintness, allowing researchers to construct a richer map of the universe's contents and better understand how the observable boundary is defined. The concept of the observable universe also challenges intuition. It is not a sphere of space surrounding Earth, but a region defined by perspective. Every point in the universe has its own observable horizon, just as we do. A distant galaxy would see its own patch of the cosmos, and the light we observe from it is only a fraction of the story. This realization shifts the notion of the edge from a literal boundary to a perspective-dependent limit, emphasizing that the universe may extend infinitely while our view remains confined. Recent missions have pushed the observable limit further than ever before. The Hubble Space Telescope, launched in 1990, revealed galaxies forming just a few 100 million years after the Big Bang. Observations continue with the James Webb Space Telescope, which detects the faint glow of the earliest stars and galaxies, refining estimates of how quickly matter coalesced into the structures we see today. Each discovery is a window into the past, showing how the observable universe is a dynamic record of cosmic evolution, rather than a static collection of objects. Within this immense volume, scientists also study subtle signals left by the universe's earliest moments. The cosmic microwave background, mapped in detail by the Planck satellite, traces tiny fluctuations in temperature that hint at the distribution of matter in the first 380,000 years after the Big Bang. These variations provide a blueprint for the large-scale structures that followed and help cosmologists predict what might exist just beyond the light that has reached us. The observable universe becomes both a map and a guide, revealing the hidden scaffolding underlying all that we see. Despite these insights, the observable universe is a reminder of limits. Galaxies beyond a certain distance are forever beyond detection, because their light will never reach Earth, carried away by the accelerating expansion, driven by dark energy. The universe within our sight is only a fraction of the total, a chapter in a story that extends far beyond the horizon. Even as instruments improve and theories evolve, the observable universe remains a boundary defined by what we can perceive, not by what exists. Each measurement and image brings humanity closer to understanding the cosmos, yet the frontier of the observable universe continues to stretch outward, teasing hints of regions that remain just beyond the reach of light. Galaxies at the edge. The most distant galaxies are not just faint points of light. They are glimpses into the universe's infancy. Each one carries the imprint of its formation, a record of stars igniting in clouds of gas that had barely existed a few 100 million years after the Big Bang. These remote islands of light challenge both imagination and technology, pushing astronomers to the limits of observation as they seek to understand what structures emerged first and how matter organized itself in the earliest cosmic epochs. Detecting these galaxies requires patience and precision. Observatories like the Keck Observatory in Hawaii use massive mirrors and sophisticated instruments to collect photons that have traveled for billions of years. By analyzing the redshift of these faint signals, scientists can determine both their distance and the speed at which the universe is expanding around them. Each discovery reshapes our understanding of cosmic history, revealing that even in its earliest stages, the universe contained regions dense enough to form galaxies that would later evolve into the massive structures we observe today. The Hubble Space Telescope has played a crucial role in revealing the edge of what we can see. Images captured in programs such as the Hubble Ultra Deep Field expose hundreds of galaxies within a patch of sky, no larger than a grain of sand held at arm's length. Many of these galaxies existed when the universe was less than 1 billion years old, offering a direct window into the conditions and processes that governed early cosmic evolution. Their diversity in shape, size, and brightness demonstrates that galaxy formation was already complex in these distant times. Some of the galaxies found at extreme distances challenge existing theories. Observations of unexpectedly massive or bright galaxies, so soon after the Big Bang, suggest that matter coalesced more quickly than models had predicted. Astronomers in Chile, using the Atacama Large Millimeter Divided by Submillimeter Array, have identified these unusual objects, raising questions about how gravity, dark matter, and gas dynamics combine to accelerate early galaxy formation. Each anomalous discovery forces researchers to reconsider assumptions and refine simulations of cosmic growth. While individual galaxies are remarkable, their placement within the large-scale structure of the universe is equally revealing. Even at the edge of observation, galaxies form clusters and filaments, hinting at a cosmic web that stretches across incomprehensible distances. These structures are mapped by extensive surveys, such as the Sloan Digital Sky Survey, which traces the positions of millions of galaxies to reveal patterns invisible to the naked eye. At the universe's edge, this web appears faint and fragmented, yet it provides clues about how gravity and dark matter shaped the universe over billions of years. Observing galaxies at these distances is also a study in light itself. The photons arriving at Earth have been stretched by cosmic expansion, shifting visible light into infrared. This redshift allows instruments like the James Webb Space Telescope to detect galaxies too faint for older telescopes, pushing the boundary of the observable universe even further. By capturing these signals, scientists reconstruct the evolution of galaxies from their earliest stages to the formations we recognize in the nearer universe, creating a continuous narrative of cosmic growth. Even as technology improves, some galaxies remain beyond reach. They recede so quickly that their light may never arrive, carried away by the accelerating expansion driven by dark energy. This creates a dynamic frontier, where each observation is both a discovery and a reminder of limits. The edge of observation becomes a threshold, where the known universe meets regions forever invisible, defined not by walls or borders, but by the interplay of space, time, and light. Studying these galaxies also informs our understanding of cosmic history and the forces that govern it. By examining the oldest star clusters, elemental composition, and rates of star formation, astronomers infer the processes that shaped galaxies over billions of years. Gazing at the farthest reaches of space feels like reading the early chapters of a celestial saga, each image adding depth to a story that began long before humans and unfolds beyond the limits of our vision. Each faint galaxy captured at the farthest reaches of space is both a signal and a question, revealing what is possible while hinting at what remains hidden. Their presence reminds us that the universe is not static, that light travels across time and expansion stretches space, and that the edge of what we observe is only the beginning of deeper exploration. As we map ever more distant galaxies, the universe increasingly suggests that beyond our current reach lie features and phenomena yet to be observed. The light travel barrier. Light is the universe's messenger, carrying stories across unimaginable distances. Every star we see and every galaxy captured by telescopes is speaking to us through photons that have traveled for millions or billions of years. Yet this communication has limits. The finite speed of light, first measured with precision by Ole Romer in 1676 while observing Jupiter's moons from Copenhagen, sets a natural boundary to what we can observe. There are regions so distant that their light has not yet reached us, creating a horizon beyond which the universe remains silent. The notion of this horizon becomes more complex when the universe itself is expanding. Objects once within reach of our telescopes can drift away faster than their light can travel toward us. Edwin Hubble's discovery in 1929 that galaxies recede from each other at speeds proportional to their distance revealed that space itself is stretching. This expansion means that some regions will never be visible, no matter how sensitive our instruments become. The light travel barrier is not just about distance, it is about the dynamic motion of the cosmos itself. As we approach this barrier, the signals we receive become fainter and more distorted. The expansion of space stretches light, shifting it toward the red end of the spectrum in a process known as redshift. Observatories like the Atacama Large Millimeter, divided by submillimeter array in Chile, detect these signals at infrared and radio wavelengths, revealing galaxies whose visible light has been stretched beyond recognition. Redshift transforms distant objects into spectral echoes, allowing astronomers to calculate their age, distance, and speed, while reminding us that these photons began their journey long before Earth even existed. The light travel barrier also shapes how we perceive cosmic time. When we observe a galaxy 10 billion light-years away, we are seeing it as it appeared 10 billion years ago. The universe captured in that image is not the universe as it exists today. Every glimpse across vast distances is a journey backward in time, revealing the evolution of stars, galaxies, and clusters. This perspective challenges our intuition, suggesting that the universe is not a single, simultaneous reality, but a patchwork of events unfolding over eons. Technology has become crucial in pushing against this barrier. Space telescopes like Hubble, and now the James Webb Space Telescope, avoid atmospheric interference, capturing photons that would otherwise be absorbed or scattered. By integrating light over extended periods, astronomers can detect the faintest glimmers from the edge of observation. Each new detection expands our understanding of the early universe, showing galaxies forming, merging, and evolving in ways that illuminate the processes shaping the cosmos. Regardless of technological gains, cosmic expansion and the finite span of time define a fundamental observational limit. Some galaxies are moving away faster than light can traverse the expanding space between us, rendering their light forever unreachable. The boundary defined by this phenomenon is not fixed. It grows and shifts with the universe's ongoing expansion. The light travel barrier thus represents a moving edge, a line that separates the observable from the forever hidden. Studying this frontier also informs our understanding of dark energy, the mysterious force accelerating the universe's expansion. Observations of supernovae in the late 1990 by teams led by the University of California, Berkeley, and the Australian National University revealed that distant galaxies are receding more rapidly than expected. This acceleration affects the light travel barrier, determining which regions will remain visible and which will vanish from view. even if their light has already begun its journey toward us. Rather than simply limiting us, the light travel horizon provides a means to glean scientific insight. By measuring how light is stretched and delayed, astronomers reconstruct the universe's expansion history, map the distribution of matter, and refine models of cosmic evolution. It also highlights a profound truth: the universe we see is only a fraction of what exists, and our observations are limited by fundamental physical laws that govern the propagation of light. Every photon arriving from the edge of this boundary is a messenger from the past, a record of events that shaped galaxies long before Earth formed. These distant signals remind us that observation in cosmology is as much about patience and interpretation as it is about detection. The universe communicates with subtlety, revealing its story one photon at a time, while leaving entire regions beyond comprehension. Even as we catch faint photons from the edge of the observable universe, they hint at regions whose light may never reach us, suggesting that what lies beyond continues to expand faster than we can follow. Dark energy and the expanding frontier. The universe is not only expanding, it is accelerating. In the late 1990 seconds, two independent teams of astronomers studying distant supernovae noticed something startling. The discovery, led by researchers from the University of California, Berkeley, and the Australian National University, introduced a new and mysterious force into cosmology: dark energy. Invisible, pervasive, and poorly understood, dark energy now dominates the universe's energy content and dictates how its expansion unfolds. Dark energy's effects are subtle yet profound. It does not emit light or interact with matter in the ways ordinary forces do, but it exerts a pressure that stretches space itself. By studying type Ia supernovae, which serve as reliable distance markers, astronomers can calculate how the expansion rate has changed over billions of years, confirming that the universe is not just growing, it is accelerating outward into ever more distant realms. This accelerating expansion reshapes how we understand cosmic boundaries. Regions that are already at the edge of observation move away faster over time, meaning their light may never reach us. The observable universe becomes a shifting frontier, constantly redefined by the interplay between light, space, and the unseen force propelling galaxies apart. Studying dark energy requires precise instruments and innovative techniques. Telescopes such as the Hubble Space Telescope have been used to gather light from distant galaxies and supernovae, while ground-based surveys like the Dark Energy Survey in Chile map vast swaths of the sky to track cosmic expansion patterns. These observations help scientists quantify the strength of dark energy, offering glimpses into how it governs the universe on scales far larger than any cluster or supercluster, shaping the cosmic web that binds galaxies across billions of light-years. Theoretical physics tries to explain what dark energy might be. Some hypotheses suggest it is a property of space itself, a constant energy density inherent in the vacuum, as Albert Einstein once proposed with his cosmological constant. Other models speculate it could be linked to exotic fields or particles yet to be discovered. While experiments have ruled out some possibilities, the true nature of dark energy remains elusive, presenting a puzzle that drives both observational and theoretical research across institutions worldwide. Dark energy also redefines our perspective on the universe's long-term future. As it continues to accelerate expansion, galaxies that are currently visible will eventually slip beyond the horizon. Clusters of stars and distant nebulae will fade from sight, leaving only the local neighborhood of the Milky Way bound together by gravity. This paints a universe that becomes increasingly empty and isolated over unimaginable timescales, where the expansion driven by dark energy shapes not only what we see now but also what future civilizations might observe. The implications extend even further, challenging cosmologists to reconsider the very structure of space-time. Dark energy interacts with the geometry of the universe, influencing whether it will expand forever, slow, or follow patterns we have yet to understand. Observations from satellites such as Planck, which map the cosmic microwave background, provide indirect evidence about dark energy's influence in the early universe. While dark energy dominates cosmic expansion, it is deeply entwined with other cosmic phenomena. Its interaction with dark matter, the invisible scaffolding supporting galaxies, shapes how structures form and evolve. Simulations run on supercomputers incorporate both components, producing models of cosmic evolution that stretch to the limits of imagination. These virtual universes offer insights into how the accelerating frontier might evolve, showing patterns and possibilities that remain unreachable to direct observation, but are essential for understanding the cosmos as a whole. The accelerating universe challenges intuition and perception. Space itself is stretching faster than light can traverse it, meaning vast regions may forever lie beyond human detection. Dark energy does not merely push matter apart. It alters the stage on which the cosmic story unfolds, creating a frontier where observation, time, and distance converge. Each measurement uncovers a new layer of complexity, revealing that the universe's edge is not a static line but a dynamic, evolving frontier shaped by forces that remain mysterious. The more astronomers map this expansion, the clearer it becomes that dark energy is not a distant curiosity, but the driving force defining the cosmos itself. Its presence transforms the universe from a static backdrop into a living, accelerating arena, where the observable frontier continuously stretches toward realms we may never reach. Cosmic expansion pushes the universe forward with a detectable yet mysterious power, hinting at regions eternally beyond our reach. Cosmic inflation and the infinite beyond. The earliest moments of the universe were unlike anything we experience today. In the 1980s, physicist Alan Guth proposed a radical idea to explain puzzling features of the cosmos: cosmic inflation. According to this theory, within a tiny fraction of a second after the Big Bang, the universe expanded exponentially, growing from subatomic scales to a vast expanse in less than a trillionth of a second. This sudden expansion smoothed the fabric of space and spread matter and energy uniformly, laying the groundwork for the galaxies, stars, and planets that would follow. Inflation also offers a solution to questions that had long troubled cosmologists. Observations of the cosmic microwave background, a faint glow left over from the universe's birth, revealed a remarkable uniformity across regions that could never have been in contact if the universe had grown steadily from the Big Bang alone. Guth's inflationary model suggested that these areas were once close together before the rapid expansion carried them far apart. The theory connected mathematical predictions with observable evidence, giving scientists a way to understand the universe's large-scale uniformity. The implications of inflation extend far beyond smoothing space. If the universe expanded so rapidly, regions beyond the observable universe could be vastly larger than what we can see. Some versions of the theory suggest an almost infinite cosmos, where inflation continues in pockets beyond our view, creating bubble universes that might operate under different physical conditions. This concept, though speculative, challenges the notion of a single, finite universe and introduces the possibility that what we see is just a small part of a far grander reality. Evidence for inflation comes from precise measurements of the cosmic microwave background. Satellites like the Planck Observatory, launched in 2009 from Europe's Guiana Space Center, mapped tiny fluctuations in this background radiation. These variations reveal the initial seeds of galaxies and clusters, supporting the idea that inflation amplified quantum fluctuations into the structures we observe today. Each pattern, captured in the microwave sky, is a record of the universe's earliest moments, offering a direct line of sight to a time beyond normal comprehension. The theory also invites reconsideration of time and space themselves. During inflation, distances grew so quickly that the concept of near and far became relative in ways that defy ordinary experience. Quantum fields dominated the dynamics, and regions that appear empty today may contain vast amounts of energy that influenced cosmic evolution. Understanding these processes requires merging ideas from general relativity and quantum mechanics, fields that operate on scales vastly different from those we inhabit. Inflationary models also hint at the possibility of a multiverse. In some scenarios, while one region of space stops inflating and forms a universe like ours, neighboring regions may continue to expand or produce entirely separate universes. These bubbles could be separated by enormous distances, or even by dimensions we cannot perceive. While no direct observation of other universes exists, the mathematics of inflation allows for their theoretical existence, suggesting that our observable universe may be only a tiny fraction of an unimaginably vast ensemble. The exponential growth of space during inflation also provides context for why the universe appears flat. Measurements of galactic positions and cosmic background radiation indicate that, on the largest scales, space follows Euclidean geometry. Without inflation, achieving this level of flatness would require extraordinarily fine-tuned initial conditions. The rapid expansion stretches any initial curvature so drastically that the universe appears flat from our perspective, offering a natural explanation for a feature that had puzzled astronomers for decades. Inflation continues to influence the questions cosmologists ask today. How did it start? And what ended it in our region of space? What determines the properties of these bubble universes, if they exist? Experiments and observations aim to detect subtle imprints left by inflation, such as primordial gravitational waves, ripples in space-time generated during the rapid expansion. Instruments like the BICEP array at the South Pole search for these faint signals, attempting to uncover evidence from a period far beyond the reach of direct observation. Even as the theory of inflation has gained widespread support, it leaves the universe open-ended. The observable cosmos may be just one bubble in a frothing, inflating expanse, with regions beyond our sight operating under rules we cannot yet imagine. This idea challenges the human perspective, emphasizing that what we see is only a fraction of the cosmic whole, and what lies beyond could be richer, stranger, and larger than anything ever measured. The more scientists probe the early universe, the more it becomes apparent that inflation points toward a cosmos that stretches endlessly beyond perception, hinting at realms we may never glimpse yet continue to shape the universe we call home. The shape of space. Space is not simply empty, it has geometry, a shape that determines how matter and light move across the cosmos. In the early 20th century, Albert Einstein's theory of general relativity transformed our understanding of this geometry, showing that mass and energy curve the fabric of space-time. Rather than a static uniform backdrop, space is a dynamic arena, bending and stretching in response to everything it contains. Determining the universe's shape is therefore not an abstract question. It is central to understanding the fate and structure of all that exists. Astronomers look for evidence of this shape in the distribution of galaxies and the cosmic microwave background. Patterns in the background radiation, first mapped in detail by the COBE satellite in 1992, and later by the WMAP and Planck missions, reveal minute temperature fluctuations that trace the early universe's density variations. These patterns contain clues about whether space is flat like a sheet, curved like a sphere, or saddle-shaped. The data suggest that, on the largest scales, space appears remarkably flat, although slight deviations could exist beyond our observable limits. The geometry of space influences the paths of light across the universe. Light traveling through curved space bends subtly, producing phenomena such as gravitational lensing. Observatories, like the Hubble Space Telescope, have captured images where distant galaxies appear distorted by the gravity of massive clusters between them and Earth. By analyzing these distortions, scientists can measure both the mass of intervening matter and the curvature of space itself. This technique reveals that space is not uniform at smaller scales, and yet its large-scale structure remains surprisingly flat and consistent. Flat space has consequences for the universe's destiny. In a flat universe, the rate of expansion over cosmic time depends on the balance of matter, and dark energy. Too much mass would eventually slow expansion and lead to a contraction, while too little would allow it to accelerate unchecked. Observations of distant supernovae in the late 1990 confirmed that expansion is accelerating, a discovery linked to dark energy. The combination of flat geometry and accelerating expansion creates a scenario where space stretches endlessly, carrying galaxies ever farther from one another. Yet space may have subtle complexities that challenge this simple picture. Cosmologists consider the possibility of global curvature, or topology that wraps space in ways difficult to visualize. Some models suggest the universe could be shaped like a three-dimensional torus, or contain repeating patterns that make distant regions appear connected in unexpected ways. Searching for these patterns involves precise measurements of the cosmic microwave background, looking for matched circles or symmetries that could hint at a hidden structure beyond the observable horizon. The shape of space also influences how structures form over time. Clusters of galaxies, superclusters, and filaments emerge according to the curvature and density of space. Simulations run at institutions like the Max Planck Institute for Astrophysics in Germany model billions of particles to reproduce cosmic evolution under different geometries. These simulations confirm that a nearly flat universe, as observations suggest, produces a cosmic web resembling what astronomers see, with vast voids separated by filaments where galaxies accumulate. Understanding space's shape intersects with the study of inflation. Cosmic inflation predicts that any initial curvature would have been stretched to near flatness, explaining why the universe appears so uniform. Yet slight deviations could remain, offering a rare window into physics, operating at energies far beyond those accessible on Earth. Detecting these deviations requires both extreme precision and novel techniques, pushing astronomers to the limits of current technology and encouraging new approaches to measuring cosmic structure. Though the universe is overall flat, local variations give rise to a vibrant and ever-changing cosmos. Matter clumps under gravity, light bends, and the interplay of dark energy and dark matter shapes the large-scale structures that define our observable universe. Space itself becomes a stage for forces and matter, where geometry is not merely a mathematical curiosity, but a fundamental influence on how galaxies, stars, and planets emerge and interact. The investigation into space's shape is ongoing, and each discovery opens more questions than it resolves. While current evidence points toward flatness, subtle curvature, or hidden topologies could lie just beyond observation, waiting for future instruments to detect them. Evidence from cosmic geometry points to unseen structures, suggesting that the universe's true form reaches well past the edge of what we can see. Dark matter's hidden hand. Galaxies spin in ways that defy expectation. In the 1970, astronomer Vera Rubin, working at the Lowell Observatory in Flagstaff, Arizona, measured the rotation speeds of stars in spiral galaxies. She discovered that stars at the outer edges moved just as quickly as those near the center, contrary to what visible matter alone would predict. Something unseen, a hidden mass, must be exerting a gravitational pull. This invisible component became known as dark matter, a substance that shapes the universe yet remains undetectable by ordinary light. Dark matter does not interact with electromagnetic forces, which is why it cannot be seen through telescopes. Its presence is inferred only through gravitational effects on visible matter, radiation, and the large-scale structure of the cosmos. Observatories around the world, including the European Southern Observatory in Chile, continue to map galaxy rotations, cluster dynamics, and gravitational lensing to understand how this hidden matter organizes itself. These observations show that dark matter forms halos around galaxies, anchoring stars and influencing their motion in ways we can measure, even if the particles themselves remain elusive. The influence of dark matter extends far beyond individual galaxies. It is the scaffolding of the cosmic web, the vast network of filaments connecting clusters and superclusters across billions of light-years. Without this hidden mass, galaxies would not have formed as efficiently, and the universe would appear far emptier. Simulations at institutions like the Kavli Institute for Cosmology in Cambridge recreate the evolution of these structures under the influence of dark matter, revealing how it guides the formation of cosmic filaments, voids, and dense nodes where galaxies cluster. Gravitational lensing offers a striking demonstration of dark matter's hidden presence. When light from a distant galaxy passes near a massive cluster, it bends, creating arcs and distortions that are visible through powerful telescopes. These lensing effects allow scientists to map the distribution of both visible and invisible mass. In 2006, the Hubble Space Telescope helped chart a massive cluster, revealing concentrations of dark matter that were offset from the luminous gas, showing that this unseen force has its own structure and movement, independent of ordinary matter. Even on smaller scales, dark matter exerts a quiet but profound influence. It affects the motions of satellite galaxies, the dynamics of galaxy mergers, and the stability of galactic disks. Research conducted at the Max Planck Institute for Astrophysics shows that the interplay between dark matter and ordinary matter shapes star formation rates, regulates galactic growth, and determines how clusters evolve over billions of years. Although invisible, it is a central actor in the cosmic story, subtly directing the evolution of the structures we can observe. Attempts to detect dark matter directly have led to ambitious experiments deep underground, where detectors are shielded from cosmic rays and background radiation. Facilities such as the Gran Sasso National Laboratory in Italy and the Sanford Underground Research Facility in South Dakota aim to capture rare interactions between hypothetical dark matter particles and ordinary matter. Though no definitive detection has yet been made, these efforts continue to refine our understanding of what dark matter could be, narrowing the range of possibilities for its composition and properties. The existence of dark matter also informs cosmology on the largest scales. It is estimated to account for roughly 27% of the universe's total mass energy content, dwarfing the fraction contributed by ordinary matter. Its gravitational pull, combined with the repulsive effect of dark energy, shapes the expansion history and large-scale evolution of the universe. Observations from satellites, such as Planck, and experiments like the Dark Energy Survey, help cosmologists link the distribution of dark matter with the growth of cosmic structures over billions of years. The study of dark matter raises profound questions about the fundamental nature of reality. If most of the universe is composed of matter we cannot see, how does that influence our understanding of space, time, and the forces that govern them? Researchers explore alternative theories, such as modifications of gravity, but so far, dark matter remains the most compelling explanation for the gravitational anomalies observed in galaxies and clusters. Its unseen hand continues to shape the cosmos in ways we are only beginning to comprehend. From sprawling galaxies to delicate cosmic filaments, all are shaped, at least in part, by this unseen power. Dark matter is invisible, yet its gravitational influence pervades every corner of the universe we can study. Its presence is subtle, yet unmistakable, guiding the formation of structures and the motion of stars across unimaginable distances. Invisible matter subtly tugs at the universe, hinting at vast domains that shape the structure of everything we observe. The multiverse hypothesis, what we call the universe, could be just one of an endless number of realms. The idea of a multiverse arises naturally from cosmological theories, particularly the concept of cosmic inflation. Physicist Alan Guth proposed inflation in the 1980, suggesting that the universe expanded exponentially in its first fractions of a second. Some versions of inflation imply that while one region stops inflating and forms a universe like ours, other regions continue to expand, producing separate, self-contained universes. These bubble universes could be governed by different physical laws, dimensions, or constants, creating a cosmos far larger and stranger than anything we can directly observe. The multiverse concept has roots in quantum mechanics as well. Hugh Everett III introduced the many worlds interpretation in 1957, suggesting that every quantum event branches into parallel realities. In this view, every possible outcome of every interaction exists in some branch, creating an ever-growing tree of universes. While Everett's ideas initially received skepticism, they now form a framework for thinking about how quantum processes might give rise to multiple, coexisting realities alongside the universe we inhabit. Evidence for the multiverse remains indirect. Observations of the cosmic microwave background, the afterglow of the Big Bang, show slight irregularities that some researchers speculate could be signatures of collisions with other universes. Teams analyzing data from satellites like Planck in 2009 searched for circular patterns or anomalies that could not be explained by standard cosmological models. While these hints are far from definitive, they inspire rigorous debate and innovative methods to probe the boundaries of what is observable. The theoretical appeal of the multiverse also lies in its ability to address fine-tuning problems. The physical constants of our universe, such as the strength of gravity, the mass of the electron, or the rate of cosmic expansion, appear remarkably precise to allow the formation of stars, planets, and life. If countless universes exist, each with its own parameters, our universe may simply be one that happened to support complexity. This perspective reframes questions of cosmic coincidence, suggesting that what seems improbable may be inevitable in a vast ensemble of realities. Mathematical models explore different types of multiverses. Some propose an infinite space, where regions beyond our observable horizon form independent universes with slight variations. Others, based on string theory, envision universes arising from compactified extra dimensions, each with unique properties dictated by the geometry of those dimensions. These models are challenging to test, but they provide a consistent framework to explore what might lie beyond the observable cosmos and why our universe possesses its particular laws. Philosophical implications are profound. If multiple universes exist, the notion of uniqueness becomes complicated. Every discovery in physics and astronomy could represent just one possibility among countless others. Questions about causality, probability, and the meaning of observation take on new dimensions when every outcome may exist somewhere. Scientists and philosophers alike wrestle with how to interpret data, define predictions, and even frame scientific reasoning in a multiverse context. Though still conjectural, the pursuit of knowledge goes forward. Experiments in cosmology, particle physics, and high-energy astrophysics test aspects of the theories that give rise to multiverse predictions. Gravitational waves, quantum fluctuations, and cosmic background measurements provide indirect windows into conditions that might favor multiple universes. Each observation, no matter how subtle, helps refine the models, showing where our universe fits within a potentially vast and varied cosmic ensemble. The multiverse hypothesis also inspires new questions about human understanding and observation. If other universes exist, they may be forever unreachable, beyond the speed of light, and isolated from our causal reality. Yet contemplating their existence changes how scientists conceptualize the origin and evolution of our own universe. It encourages the development of bold mathematical frameworks and imaginative experiments, bridging the boundaries between physics, cosmology, and philosophy in the search for deeper truths. Unproven as it is, the hypothesis offers a glimpse into phenomena that lie beyond the reach of our instruments. The notion that our universe might be just one bubble in an endless foam challenges our perception of reality and invites exploration into realms that stretch the imagination and the laws of science. The cosmos may be far larger, stranger, and more varied than anything we can observe, hinting at countless unseen worlds beyond the reach of light, simulating the unseen. While the cosmos extends far beyond comprehension, scientists can digitally model its evolution. Simulations of cosmic structure have become indispensable for understanding phenomena that cannot be observed directly. Starting in the late 20th century, researchers began using powerful supercomputers to model the formation of galaxies, clusters, and filaments, translating mathematical equations of gravity, dark matter, and gas dynamics into virtual universes. These simulations allow scientists to explore the unseen scaffolding of the cosmos and test hypotheses that cannot be examined in a laboratory. Simulating the cosmos requires both immense computational power and careful attention to detail. The Millennium Simulation, conducted by the Max Planck Institute for Astrophysics in Germany in 2005, tracked the evolution of over 10 billion particles, representing dark matter and baryonic matter across billions of light-years. The results produced a virtual cosmic web, a dense network of filaments and voids that mirrors structures seen in observational surveys. By comparing these simulations with telescope data, astronomers can validate theories about galaxy formation, dark matter distribution, and large-scale cosmic expansion. The inclusion of dark matter is critical to these models. Invisible yet dominant, dark matter shapes the formation of galaxies by creating gravitational wells that attract gas and stars. Simulations reveal how these halos merge and interact over billions of years, producing structures observed in the night sky. Researchers at institutions such as the Kavli Institute in Cambridge have refined their models to include both dark matter and dark energy, allowing simulations to capture the accelerating expansion and its effects on cosmic architecture. Gas dynamics and star formation add further complexity. Computer models must account for how gas cools, collapses, and ignites nuclear fusion in stars, as well as the impact of supernova explosions and stellar winds. Projects like Illustris, a collaborative effort launched in 2014 by a team of international researchers, simulate these processes in detail. The resulting virtual universes provide insights into the formation of spiral galaxies, elliptical galaxies, and the distribution of stars within clusters, revealing patterns that help explain why the observable universe looks the way it does. Extreme conditions that defy earthly reproduction become accessible through simulations. Black holes, for instance, influence their surroundings through gravitational pull and energetic jets. By modeling these interactions, scientists can study how supermassive black holes shape galactic centers and regulate star formation. These virtual experiments allow researchers to trace the life cycle of galaxies from their earliest formation to their current state, offering a view of cosmic evolution that no telescope alone could provide. Predictive power is another key feature of simulations. By adjusting parameters such as the amount of dark matter or the rate of cosmic expansion, researchers can test how changes would affect galaxy formation and distribution. These experiments are invaluable for planning observational campaigns, helping astronomers know where to look for distant galaxies or how to interpret anomalies in data. The synergy between simulation and observation accelerates discovery, turning computers into laboratories for the universe itself. Beyond what telescopes can capture, simulations let us explore hidden cosmic realms. While telescopes are limited by the distance light can travel, computer models can extend hypothetical conditions far beyond the cosmic horizon. Researchers can investigate how inflation, dark energy, and variations in physical constants might influence structures in regions we cannot see. These virtual explorations push the boundaries of what we can study, revealing possible realities that remain forever beyond observation. The collaborative nature of these projects is notable. Scientists across the globe share data, code, and models, refining simulations with the latest theoretical and observational insights. High-performance computing centers in Germany, the United States, and Japan contribute to these efforts, enabling simulations that involve trillions of calculations. Each new iteration brings virtual universes closer to reality, offering ever more detailed and accurate representations of the cosmos. Ultimately, simulating the unseen transforms abstract equations into living, evolving universes. Galaxies emerge, clusters form, and the cosmic web stretches across the virtual sky, all shaped by forces and matter we cannot directly perceive. By creating these digital analogs, scientists gain intuition, test theories, and explore scenarios that observational astronomy alone cannot reveal. Advanced simulations only hint at phenomena and realms beyond their scope, indicating the universe contains structures and dynamics yet to be conceived. Cosmic shadows and ghost light. Light lingers subtly, even in the emptiest reaches of the cosmos. Astronomers have long known that the universe is not entirely dark, even where stars and galaxies are scarce. Faint radiation, relics from the early universe, drifts through the cosmos as a diffuse glow. This is the cosmic background, light that has traveled nearly 14 billion years, carrying with it the imprint of a universe in its infancy. It is a ghostly illumination, a shadow of events that occurred when matter and energy first began to coalesce into the structures we see today. Some of the faintest light comes from intergalactic dust and gas. While tenuous, these clouds scatter and absorb photons, subtly influencing the brightness and color of distant galaxies. Observatories, such as the European Southern Observatory's Very Large Telescope in Chile, measure these effects, helping astronomers correct observations and understand the distribution of matter between galaxies. Even invisible matter leaves traces in the way light bends, shifts, or dims, offering indirect clues about the unseen components of the cosmos. Gravitational lensing provides another form of cosmic shadow. Massive clusters warp space-time, bending light from galaxies behind them into arcs and distortions. This phenomenon not only magnifies distant objects, but also maps the distribution of dark matter, revealing concentrations of mass where nothing is visible. The Hubble Space Telescope and the Subaru Telescope in Hawaii have captured stunning images of these lenses, transforming the way scientists see the architecture of the universe. Shadows, in this sense, become a tool for discovery, rather than an absence of light. Rare cosmic events generate light that the universe casts so subtly that it is barely observable. Supernovae, for instance, briefly outshine entire galaxies, yet their remnants gradually fade into ghostly traces. Even gamma-ray bursts, among the most energetic events in the cosmos, leave faint afterglows detectable only with sensitive instruments like NASA's Swift Observatory. These ephemeral signals serve as cosmic breadcrumbs, illuminating processes that occur across billions of light-years and offering a glimpse into the violent and transient phenomena shaping galaxies. The unseen forces of dark matter and dark energy contribute their own forms of shadow to the cosmos. Dark matter, though invisible, exerts a gravitational pull that alters the trajectories of light and matter, creating distortions that can be measured. Dark energy, which drives the accelerating expansion of the universe, stretches space itself, diminishing the intensity of light from distant objects over time. Together, these hidden forces shape how light reaches us, emphasizing that much of the cosmos is revealed not by what is visible but by the subtle ways it influences what we can see. Infrared and radio telescopes uncover forms of ghost light that optical instruments cannot detect. Dust-enshrouded star-forming regions glow in infrared, while synchrotron radiation from charged particles moving in magnetic fields is visible in radio frequencies. Facilities, such as the Atacama Large Millimeter, divided by Submillimeter Array ALMA, in Chile capture these signals, revealing galaxies and structures that remain invisible in ordinary light. Each detection expands our understanding of the universe, showing that light exists across a spectrum far broader than human vision allows. Absolute darkness does not exist, even in the emptiest stretches of the cosmos. Minute traces of background radiation and scattered light permeate these regions, a testament to the universe's pervasive energy. Satellites like Planck and the Wilkinson Microwave Anisotropy Probe have measured these faint signals, mapping variations that correspond to the seeds of galaxy formation. In this way, cosmic shadows carry information about the universe's past, encoding the history of matter, energy, and the processes that sculpted the cosmos. Studying these faint signals requires both patience and innovation. Instruments must eliminate interference from Earth's atmosphere and local sources of light, while algorithms extract meaningful patterns from noise. Teams at institutions, such as the Kavli Institute for Cosmology, refine their methods continually, revealing subtle structures in the background glow that hint at hidden galaxies, interstellar gas, and even the influence of dark matter. Each faint detection brings the universe into sharper focus, revealing layers of reality previously hidden in shadow. Ghost light and cosmic shadows remind us that the universe is never truly empty. Light that has traveled billions of years carries the signatures of distant events, invisible matter, and processes beyond direct observation. By interpreting these faint signals, astronomers trace the invisible threads that shape the cosmos and uncover realms that remain just beyond reach. In the faint reaches of the universe, these soft glimmers point to hidden forces and structures, inviting us to look beyond the visible horizon. Philosophy of the cosmic edge. The concept of a cosmic edge challenges not only physics but also human perception. Philosophers and scientists alike have long grappled with what it means to imagine a boundary to everything that exists. In the 20th century, thinkers such as Henri Bergson and later Carl Sagan pondered the limits of space and time, recognizing that the universe stretches both imagination and intellect. The very idea of a beyond provokes questions that cannot be answered by observation alone, pushing inquiry into abstract reasoning and philosophical reflection. Space may extend infinitely, or it may curve back on itself, creating a universe without borders. Mathematicians and cosmologists explore these possibilities through models of geometry and topology, considering spherical, hyperbolic, and flat spaces. These models suggest that the universe could be finite yet unbounded, meaning it has a measurable volume, but no literal edge. Such concepts force a reconsideration of what an edge truly implies, revealing that the limits we imagine are often artifacts of perception rather than physical reality. The edge of the universe also evokes questions about existence itself. If there is a boundary beyond which nothing is observable, does that region have meaning? Philosophers like Immanuel Kant speculated on the noumenal realm, realities beyond human perception, and these ideas resonate with cosmological boundaries. Scientists encounter similar issues when discussing regions beyond the observable universe, where light has not yet reached us. In both cases, human knowledge confronts its limitations, prompting reflection on what can be known and what must remain speculative. Recent studies of the cosmic microwave background suggest subtle anisotropies that could hint at regions beyond what we can observe, reinforcing the philosophical question of what lies beyond perception. Our place in the cosmos shapes the way these philosophical questions are framed. Humanity occupies an infinitesimal corner of space and time, yet we seek understanding of the universe as a whole. This tension between scale and comprehension echoes through history, from the heliocentric revolution, led by Copernicus in the 16th century, to the development of general relativity by Albert Einstein in 1915. Each breakthrough expanded the horizon of what could be observed, and at the same time, revealed new layers of the unknown, highlighting the interplay between discovery and humility. Cosmology and philosophy intersect in the contemplation of time at the universe's edge. Time, as measured by the expansion of space, flows differently depending on relative motion and gravitational forces, a concept formalized in Einstein's theories of relativity. As we project outward toward the farthest reaches, the flow of time and the perception of events blur, raising questions about causality and existence. The concept of multiverses, supported by some interpretations of quantum mechanics and inflationary cosmology, adds another layer to the philosophical debate about cosmic boundaries and the nature of reality. These considerations challenge intuitive notions of beginning and end, suggesting that the universe may operate on scales beyond ordinary human understanding. Ethical and existential implications emerge when considering a universe with an edge or multiple edges. If vast regions lie forever beyond observation, it raises questions about significance and meaning. Philosophers, theologians, and scientists alike confront the human need for context in an expansive cosmos. The pursuit of knowledge, from mapping distant galaxies to simulating cosmic evolution, becomes a way to situate ourselves within an immense and possibly infinite reality, bridging observation with reflection. The search for the edge of the universe parallels the exploration of knowledge itself. As telescopes and detectors reach further into space, every discovery prompts new questions. Satellite missions, such as the Hubble Space Telescope and the James Webb Space Telescope, extend our perception, revealing structures and phenomena previously inaccessible. Yet each observation also exposes the limitations of measurement and understanding, reminding us that the pursuit of the edge is as much a philosophical endeavor as a scientific one. Historical attempts to visualize the universe's edge, from medieval maps depicting seas and unknown lands to early 20th century artistic interpretations of space, reveal humanity's long-standing fascination with boundaries beyond reach. Ultimately, contemplating the cosmic edge is an exercise in perspective. It forces consideration of scale, of what it means to observe, and of the distinction between the observable and the unobservable. By grappling with these questions, scientists and philosophers alike expand not only our knowledge of the universe, but also our understanding of human thought, curiosity, and the desire to confront the unknown. Boundless and elusive, the universe hints at edges that are only imagined, inspiring exploration of the nearly unreachable. The edge, as a story, unfinished. All its immensity aside, the universe resembles a story still being told. Every observation, from Edwin Hubble's discovery of galactic redshifts in the 1920s to the latest images captured by the James Webb Space Telescope, adds new sentences to this story. Yet for every revelation, countless questions remain, as though entire chapters exist beyond the reach of our instruments and understanding. The edge of the cosmos is not a wall, but a page turned just out of sight, inviting contemplation of what lies beyond. Exploring the edge demands imagination grounded in science. The observable universe stretches nearly 93 billion light-years across, yet beyond that horizon lies territory we cannot perceive, where light has not yet reached us. This limitation turns every measurement into a fragment of a larger tale, a chapter that hints at unseen structures and phenomena. Cosmologists like George Smoot, whose work on the cosmic microwave background earned him the Nobel Prize in 2006, have shown how tiny fluctuations in primordial light can narrate the earliest chapters of the cosmos, offering clues about forces that shaped everything that followed. Sophisticated though they are, telescopes glimpse only a portion of the cosmic tale. Observatories such as ALMA and the Hubble probe deep into space, yet the light they capture comes from distant eras, not from the present state of far-off regions. This delay transforms astronomy into a form of time travel, allowing scientists to read the history of galaxies, stars, and cosmic webs. Each photon carries a message from billions of years ago, a sentence in a story whose ending remains unknown. Observing these signals is like tracing the plot of a novel whose final pages have yet to be written. Complementing what we observe, simulations allow us to explore situations that cannot be seen firsthand. Projects such as the illustrious TNG simulation recreate the formation and evolution of galaxies, superclusters, and cosmic filaments across billions of years. By comparing these models with real data, scientists gain insight into processes otherwise hidden, from dark matter dynamics to the influence of supermassive black holes. Yet even simulations are limited by assumptions and computational power, reminding us that the story of the universe is always provisional, never complete. Theories of the multiverse suggest the story may be far more complex than a single narrative. Cosmic inflation and quantum mechanics hint that our universe could be one of many, each with its own unfolding history and physical laws. While these ideas remain speculative, they challenge the notion of a single closed story and invite contemplation of parallel tales playing out beyond the scope of our instruments. If these other universes exist, the edge is not a boundary, but a junction to other narratives, each with its own mysteries and surprises. Philosophical reflection deepens our engagement with the cosmic story. Thinking about beginnings and endings, about what can be known and what remains hidden, connects scientific inquiry with human curiosity. From early cosmologists to contemporary thinkers, the question of what lies beyond perception has inspired both measurement and speculation. The edge of the universe, then, becomes a mirror for our quest for understanding, showing the limits of observation while illuminating the boundless scope of inquiry. Historical attempts to imagine the cosmic edge reveal a long-standing human desire to frame the unknown. From medieval maps that depicted terra incognita at the boundaries of known lands to early 20th century artistic renderings of infinite space, humanity has continually sought to visualize what lies beyond immediate perception. These cultural and intellectual endeavors illustrate that the story of the universe is not only scientific, but also narrative, aesthetic, and philosophical. Each attempt to picture the unseen contributes a verse to an ever-expanding poem. Ultimately, the edge of the universe is less a terminus than an invitation. Every observation, simulation, and theoretical exploration adds richness to a narrative without end. Scientists read the universe like a manuscript in progress, discovering patterns, uncovering anomalies, and revealing histories written in light and gravity. The story is unfinished, and every discovery reminds us that the cosmos extends beyond what we can grasp, urging us to continue turning the pages. As we theorize and observe, the edge remains a frontier to hidden narratives, a place where the universe continues its tale.